one more comment in before we all take off for a lovely Thanksgiving holiday weekend. And that's, well, getting a lot of questions on problem 10. Not surprising. It's a challenge problem. And this is not actually too hard of a physics problem, but it requires some kind of clever thinking on mathematics. And what I wanted to do is kind of set this up for you. So you see where the math might come together. This force field is kind of a weird force field because it depends on your x and your y position, and it's acting in different directions depending on where you are. Now, what we can do is I'm going to think about, first I want to do path 2. So path 2 actually has two components. Walk horizontally, then you walk vertically. So I want to calculate the path along path 2, or the work along path 2, and that's going to be equal to the force in the x direction times the displacement in the x direction as we go from this point here out to here. And then I'm going to do a force in the y direction times the displacement in the y direction as we go over step 2. So I'm going to let's call that step A and step B. So here's A and here's B. Well, what's the force in the x direction here along the x-axis? Well, that says that the force in the x direction is equal to C0 times y plus C1. Okay, it's just a number. I don't know what your numbers are, but mine are just these letters. And for the x-axis, y equals 0. Therefore, this is equal to C1. And therefore, the work along this path A is just C1 times 2 meters. Right? 2 meters, constant force, awesome. Okay, how about the second path? So for B, we have the force in the y direction. That's C2x3 times the displacement in the y direction. So that's C2 times x plus C3 times the displacement in the y direction. That y direction version is just 1 meter. C2 is times x. But what's x here? Oh, look at this. It's 2 meters. So C2 times 2 meters plus C3. Yeah, I'll be able to figure that out. Everything's given in this problem. Just calculate it out. And that's the full path along work along path 2. It's just the sum of these two numbers. Pretty slick. So then what we've got to do is go along path 1. And path 1 is the evil path because it is neither in the x nor the y direction. So for path 1, it's kind of like climbing a hill. And if we think about it, there's a distance along that path going up this way. And each point in that path has a x and a y point associated with it. So there's my y, and this thing here is another variable. That's totally not a curly bracket, but whatever. I'm going to call this variable s. And we know a lot about s, especially in relationships to x and y, because it's a fixed line, and all the way out here, I know that if I go 2 meters in the x direction, I go 1 meter in the y direction, and s runs from 0 to the square root of 2 squared plus 1 squared, which is equal to root 5. So I know that the displacement along the path is going to be root 5 meters total. And at that point, what I do is I say, well, I'd like to figure out what the force is along that path. Well, that is it's kind of a little tricky, but I can figure out what the sum of the x force is and the y force. I'm going to not go all the way from here, but I will note that we have one more relationship between x and y, and that is that I can write down s well, I can write down x as whatever s is, and it's going to be the fraction of the distance in the x direction. You can figure this out from cosines and sines and stuff like that, but we know also just from just straight geometry that that's s times the square root of 4 over 5, which is also equal to 2 s over root 5. And if I need to, I can go ahead and plug that into my force equation up here. Similarly, I can write down y as the expression of s times the square root of 1 over 5, or s over root 5. So what's nice about this is I can use this relationship here, which just comes out of geometry and the nature of these triangles, that or the ratios embedded in these triangles, to eliminate the x's and y's from my force equation and replace them with just a force projected along this path. So that's kind of cool. And then what I can do is I can say, well, then the force dotted along this path is just going to be is just going to be expressed entirely in terms of s. And you should end up with an expression that has a big bunch of constants. So then you're going to end up with a force along s is going to be a big bunch of constants, mess, times s plus another mess. And you can figure these things out just from some algebra, but you know how to solve these forces. You know that the work associated with this is just the work associated with a spring. So it should be 1/2 k, where the mess here is k, times s squared, and that's the work for that. And then this one is just the constant force, so it's just the force times the distance. So you know all of these things, and this just looks like a spring plus a constant force. You might not realize it from this crazy formulation up here, but really all it is just some algebra. It's algebraically identical to all the problems that we've been solving before. So I hope that this all gives you a little bit of a hint of where to go here. There's a little bit of trickiness associated with projecting the force along this direction, but I'll leave you to think about that. But one thing that I was chewing on is that this is the same mathematical form of these forces projected kind of like on a hill, where this is your hill, and you can ask, well, what's the component of the force along the hill? So I hope that gives you all the tools that you need to crack this open, or you can say, enough physics, and go have a wonderful Thanksgiving, because, yeah, that's my plan right now. Have a great weekend.